Right, this is where we left off yesterday in our first meeting. I'll just remind you, we're looking at, in this chapter, sales data. This would be a monetary unit of measurement. Doesn't specify over here, but we can probably look at the data itself on R if we have time today, against the expenditure when it comes to three modes of advertising: TV, radio, and newspaper. As always, the big chunk of these sessions, it's just going to be me reading from this book. I will add commentary when I feel I can enhance what's written. Although, if yesterday's experience was anything to go by, this is just a lovely book, and it really trying to complement it probably does more harm than anything else. Let's get started. More generally, suppose that we observe a quantitative response. This is our output. This is what we're trying to model, Y, and P different predictors, your input variables, from x1 all the way to xp. P is, of course, an integer. We assume that there is some relationship, and this is what we're after, between y and this vector of variables. So think of every observation. I will very often take my examples from insurance. So think of the number of claims that an insurance company has on an annual basis. We would like to predict the number of claims that we're expecting next year in 2023. So that's our response variable. We're going to look at the historical data, and we will have a vector of outputs. If it's a company that's been operating these last 20 years, and we have access to the full extent of its data, then we have 20 observations. So that would be 2020, well, 2002, 2003, till this very year. So you would have 20 outputs, and you're going to tie them to one or more variables. So the number of policies that you sold, where you sold those policies, through which brokers, if there was any profit sharing between the company and the brokerage system, where perhaps we were able to encourage better better business. So those are just a few examples of the variables that, if they've been quantified, and if we have a record of these variables over the historical period that we would like to incorporate within our model, then those are going to be your x1, x2, all the way up to xp for each observation. And if we're looking at the number of claims in a single year, then the observations are the number of claims 20 years ago, the number of claims 19 years ago, all the way till the number of claims last year. So 20 observations, this will be a vector. This will be a vector. This, on the other hand, will become a matrix, because you will have an x1. So imagine x1. So the first predictor is the number of policies that were sold. Although probably a better quantifier is the premium that you received. No two policies, or it's very rare that any two policies are identical, offer the same risk to the insurance company. So instead, you would perhaps look at the premium that the policy brought in, what the policyholders paid. So you would have an X1 for the year, the very first year of your data, an X1 for the second year of your data, etc., etc., which can be written in the very general form: y is equal to f of x, and here is your epsilon. Now that's capturing the variability. Now remember, we are not trying to create a deterministic model. We're not creating a model that, and that would actually be limited. We don't want to create. We want to incorporate some of the noise within the data. So think of the noise over here. It's quite different, isn't it, to your secondary and post-secondary mathematics, where you don't have this scatter, you don't have this variability. But if without the epsilon, your model, you would visualize it simply as this solid blue line. And that would be a model that would tell you, if you spend 30 so many financial units on radio advertising, then you are definitely going to have your sales at 15 units of whatever in a given month. The epsilon is there to capture variability. And by the way, there's especially when you're working in a more senior role, designing the model, maybe it's going a bit far saying it's only a small part of the job, but it very often feels that way, at least in my case. The model, you know, that's I think anyone in this field, really, that's the easiest, or in many ways it's the easiest step. But what can be a lot more challenging is communicating the results of the model, getting members of a committee, members of the board, hey, who knows, the shareholders themselves, depending on the situation, to understand the risk. And what do we mean by risk? Well, that's the uncertainty, right? And epsilon contains that uncertainty. You need that all stakeholders have a good idea of the risk versus reward calculation. Here, f is some fixed but unknown function of the input variables, and epsilon is a random error term which is independent of x and has an average. So when we say mean, I don't know if you remember, but there are different types of averages. What do we even mean by an average? An average is when you take a list of data and you reduce it to a single value. And that value is, in one or another way, representative of the entire data set. There is median, there is mode, there is mean. They all have their place. This is not a case of one being more suitable. It depends on a number of factors, as with most things. But we need our error term, or we would like our error term to have a mean of 0. When your mean is 0, you are exactly on the line, and then you have your positive should I say that the epsilon can contribute a positive value or a negative value that will take you above or below the line. In this formulation, F represents the systematic information that X provides about Y. As another example, consider the left-hand panel of figure 2.2, and we'll go to it very soon, a plot of income versus years of education for 30 individuals in the income dataset. And before we even look at that panel, if we were to go into our studio and we said you wouldn't, I don't need to install the package now, but I definitely need to, I'm going to use the word load it, library, and what was it? Introduction to Statistical, is this it? ISLR, and we can, again, I'm going to use the word load. Was it this? Is this the wages data? Let's see, let me just double check. Another example. Yeah. And we can go into the structure, and these dots, I guess, mean that we have maybe more than, no, I think this is just, okay, yeah. No, that was just the pane was too narrow. And we can, I think yesterday we took a histogram. We took a histogram of the ages. And would this work? Let's have a look. And if it did work, we'll have the histogram over there. But I think we need to do it this way. That's your histogram. You can calculate the mean, the median, you can calculate percentiles. We're going to look at which variables. We're going to plot income versus years of education. Oh, it's actually in the income data set. So let's see if we can find the income data set. So data, income, it's not actually, doesn't seem to be there for, really need to get to grips with exactly what is contained in this. In this package. Let's have a look. Let's have a look. So ISLR, and these are the these are apparently the data sets. So what the book is referring to income, I would imagine is the wage. So let's just delete this. And we can plot, let's see what we're going to plot. We can plot the wage variable. So this is the data set, wage. Then I specify I want the wage values in the wage data set against, and we said, for example, education. Although education is a factor, I'm not entirely sure if this works. It does, but it seems to have flipped them around. Let's compare to age. And again, it's flipping them around, isn't it, for some reason? Right, because I think I've typed them, need to be typed this way. And this is, you remember this from our previous session? You have your high earners, and we had plotted, or the book plots a nonlinear trend line through the data. Okay, let's go back to the book. It's only looking at 30 individuals. Let's have a look. Okay, so I think this is very, very different to the data. Does it tell us? It's meant to be the income data set. So this is something perhaps after the session, either one of you could have a look or just remind me. Let's read it again. As another example, consider the left-hand panel of figure 2.2, a plot of income versus years of education for 30 individuals. Years of education just means how many years each observation has done at school. So you're not looking at the specific degree. In a way, I guess you could refine it. You could say, okay, years of education, but is it a STEM subject, etc. In the income data set, the plot suggests that one might be able to predict income using years of education. So there's a clear correlation, isn't there? Now you may try using linear regression. However, if we look at this diagram over here, the curve that the fitted is clearly not linear. So let's continue reading. And we were told, since income is a simulated data set. Oh, I see. Do we know what's being said over here? This is not raw data. This is not empirical data that has been collected at, I don't know, at a specific company. What the authors have done over here is they've worked backwards. What they've done is they've started with the blue line. So the F that you need to determine typically on the job in practice, they've started with a known F. They've kind of reversed the process. They've started with a known F. They've added an error term. They ran a simulation. It created one observation for someone who did 10 years in education, 11, no? Okay, so 10, I don't know, 10.2, 10.4, 10.6, 10.8, 12, etc. So what the authors have done over here is they've simulated the data set. In a way, you're playing God. You know the relationship a priori. You know it in advance. Since income is a simulated data set, F is known and is shown by the blue curve. So that's F. F is the systematic representation. The vertical lines represent the error terms epsilon. So really, epsilon is this simulation. Without epsilon, each observation would have been on this curve. Epsilon is adding the variability, the noise to the simulated data points. Now, again, in real life, you would work exactly the other way around. You would first collect the data, survey, metadata on some app. Those are the only two examples I can think of right now. And then you would fit a curve. And you would also estimate the error term. We note that some of the 30 observations lie above the blue curve and some lie below it. Overall, the errors have approximately mean 0, meaning that kind of the vertical length above cancels out or zeroizes with the vertical length below. If you want to think of this as a positive length and a negative length, I know length is never negative, but just follow my lead. The positive lengths will zeroize or basically zeroize, whatever we mean by basically, right? With the negative lengths. In general, the function f may involve and this is where it gets interesting now, or we're going to go into higher dimensional statistics. In general, the function f may involve more than one input variable, so we're allowing for more complexity. In figure 2.3, we plot again income. Income remains our output variable. We're trying to plot. We're trying to forecast, predict income. This time around, as a function of two variables, years of education and seniority. Now, what do we even mean by seniority? Let's have a look. Here, f is a two-dimensional surface that must be estimated based on the observed data. And it's lovely, isn't it? Most of us are familiar with a linear surface, so that's your plane. So linear regression, you qualify from, or you graduate from fitting a line to a set of observations to fitting a plane. That would be linear regression. Whereas over here, it's the same concept. Oh, by the way, do you realize that roughly this curve over here is the blue curve that we had earlier. This curve over here. If I only look at these two dimensions, income and years of education, then that's the curve we had on the previous page. Our model is the blue surface. It is the blue surface. And again, we have the positive lengths and negative lengths. They're going to zeroize in aggregate. What do you understand by seniority? I would imagine seniority is just the number of years you've been at the company. So think of company loyalty, think of hopping from one company to another. In essence, statistical learning refers to a set of approaches for estimating f. In this chapter, we outline some of the key theoretical concepts that arise in estimating f, as well as tools for evaluating the estimates obtained. Why estimate f? There are two main reasons that we may wish to estimate f: prediction and inference. Let's start with prediction. In many situations, a set of inputs x are readily available. And do remember, x very often is going to be a vector. It's not going to consist of a single characteristic of your data subject. But we just saw that looking at those 30 employees, looking at each data subject, we could take two characteristics of theirs. And there's that balancing act that we mentioned yesterday, which is also contingent on just the extent of the available data. In this setting, since the error term averages to 0, we can predict y using, and this is crucial notation, which may very well be new to a lot of us today. We read it as y hat. So y is the true observation. Y hat is the estimate. It's the estimate that's based on the model that you're using to understand the data to predict the output. So we may predict the output y using f hat, where f hat represents our estimate for f. So you need to think of it this way. If we were, what's the word? Not omnipotent, or is it omnipotent? If we were like godlike, And we knew everything. We knew everything. We knew the speed of every atom at every location of the universe. If we knew everything, then you would know F, assuming that such an F exists. Now, usually we know a lot less than everything. So our model, notationally, we indicate that our model probably doesn't know everything, probably doesn't get everything right, using F hat. Notice the X doesn't change. We don't give a hat to the X. Your input data remains your input data. You know your input data. If I want to predict the grade of a student who studies exactly 0 hours a day, well, there's no estimate over there. I know that that specific individual studies 0 hours a day. That's your input. That's your input. F hat is your model with its restrictions. And as a result, it's going to give you an estimate for Y. Notice that we've dropped the error term, but we've dropped the error term for the simple reason that we're talking about expectation. And expectation in statistics is represented like this, very often square brackets. So I take the expectation of the right-hand side as well. You'll be glad to hear expectation is linear. So I may take the expectation of each term individually, and this means I can drop this term because the error term is going to have a mean of 0. So what should I expect? Well, if I know F hat, which is our estimate for F, Y hat represents the resulting prediction for Y. It's what you should expect. So given that I know how many hours a person studies a day, how many hours of private lessons, if they attend school or they do not attend school, maybe they're a private candidate, with that information, and the data, your input data is always going to be limited. There is no way that you can allow for every single feature, every single characteristic of your observation. So that's what introduces limitations to your model. So this is why we have F hat, and with F hat we get Y hat. In this setting, F hat is often treated as a black box, in the sense that one is not typically concerned with the exact form of F hat, provided it yields accurate predictions for Y. So really, our priority is that Y hat is close to Y. And you're going to look at the historical data. Does this model, if I had this model at the start of when I started collecting the historical data, would it have given the same observations that actually crystallized? As an example, suppose that x1 until xp are, and we're using the same word over here, characteristics of a patient's blood sample that can be easily measured in a lab, and y is a variable encoding the patient's risk. So that might be a percentage, a likelihood, the patient's risk for a severe adverse reaction to a particular drug. It is natural to seek to predict y using x, since we can then avoid giving the drug in question to patients who are at high risk of an adverse reaction. That is, patients for whom the estimate of y is high. So you could take an interval. I mentioned percentages earlier. So take 0 as your lowest risk and 1 or 100% as your highest risk. And our model fed these characteristics attempts to give us an indication of how that risk would vary from patient to patient, depending on their underlying characteristics. The accuracy of y hat as a prediction of y depends on two quantities. Might get a bit theoretical over here, which we will call the reducible error and the irreducible error. So notice, even just from the jargon, we're recognizing there is going to be error within our predictions that, for reasons that we may see in this very session, cannot be reduced to 0. So what does that even mean? What does it mean that you cannot reduce the error to 0? When we say an error, we don't mean that in our model there's a line of code that's saying 1 + 1 is 5. The error is that our model cannot. This is no model is perfect. No model will ever give you an exact, accurate prediction for each observation. In general, f hat will not be a perfect estimate for f, and this inaccuracy will introduce some error. This error is reducible, so this is f, because we can potentially improve the accuracy of f hat. For instance, allowing for more variables, or in the book says by using the most appropriate statistical learning technique to estimate f. However, even if it were possible to form a perfect estimate for f so that our estimated response took the form y hat is equal to f of x. So see, we've dropped the hat. Our prediction would still have some error in it. This is because y is also a function of epsilon, which by definition cannot be predicted using x. Therefore, variability associated with epsilon also affects the accuracy of our predictions. This is known as the irreducible error because no matter how well we estimate f, we cannot reduce the error introduced by epsilon. Why is the reducible error larger than 0? The quantity epsilon may contain unmeasured variables that are useful in predicting y. Since we don't measure them, f cannot use them for its prediction. The quantity epsilon may also contain unmeasurable variation. For example, the risk of an adverse reaction might vary for a given patient on a given day, depending on manufacturing variation in the drug itself, or the patient's general feeling of well-being on that day. There's even, you may have heard of the placebo effect. If the patient knows that they're taking a drug, but by the sheer knowledge of knowing if you are on a program where you're taking medication, that actually can have an effect. Now, I don't want to get lost in the mathematical details, not in today's session. We will read it. Consider a given estimate, f hat, and a set of predictors x, which yields the prediction y hat is equal to f hat of x. Assume for a moment that both f hat and x are fixed. That is easy to show that is easy to show that. Now, what are we looking at over here? What we need is, we're looking at the difference between the prediction, and the actual output. And all I will say at this stage, this is not difficult to understand, by the way. It's purely algebraic logic. That this is this. We then expand this expression by squaring. You then apply the linearity of expectation, and we haven't defined this term yet. I guess the book assumes, but we can do it at a later stage. Once you apply the expectation throughout, you will get what is known as the variability of epsilon. Remember, what do we mean by variability? Just think of everyone's weight in this meeting. I doubt that we all weigh the same number of kilograms. So that means there is variability within the data set of our weights. And this is irreducible. Now, why did we even start with this term in the first place? This represents it's a very important measurement in statistics, the expected value of the squared difference. Now, you may be asking, why take the squared difference? Why isn't subtracting good enough? And no, because we like things that are positive. And if I square, I know that now this is positive, or definitely not negative. Let's put it that way. And that's really the main reason, or you can think of it as the main reason why in statistics we consider this. This is a very important measurement. Again, E is expectation. And var epsilon represents the variance associated with the error term. Now naturally, the lower your variance is, if it really is low, obviously, I mean, the model might be telling you it's low and it isn't actually low. But the closer your model is to being a deterministic one, the less uncertainty you have in the predictions that the model produces. The focus of this book is on techniques for estimating F, with the aim of minimizing the reducible error. It's what you would expect, right? If it was anything different, that should come as a surprise to us. So we want to estimate F, and we wish to minimize the variability within epsilon. It is important to keep in mind that the irreducible error will always provide an upper bound on the accuracy of our prediction for Y. This bound is almost always unknown in practice. And I'm just going to move on. Now, inference. We are often interested, so remember, it is regression and inference, I think. Prediction and inference. So prediction was what we just did. If you had to ask me what is the difference, let's have a look. Inference. So prediction is when we're looking at at what the model is outputting. Inference, we are often interested in understanding the way that y is affected as these variables change. In this situation, we wish to estimate f, but our goal, okay, interesting, is not necessarily to make predictions for y. We instead want to understand the relationship between x and y, or more specifically, to understand how y changes as a function of these variables. Now, f hat cannot be treated as a black box. I'll be honest, I am feeling slightly lost, because we need to know its exact form. In this setting, I would imagine there's so much overlap between these two, that very often I think the distinction between prediction and inference tends to blur. In this setting, one may be interested in answering the following questions. Right, exactly. Okay, it's very close to what we were saying earlier. Which predictors are associated with the response? It is often the case that only a small fraction of the available predictors are substantially associated with y. Identifying the few important predictors among a large set of possible variables can be extremely useful, depending on the application. What is the relationship between the response and each predictor? Some predictors may have a positive relationship with y, in the sense that increasing the predictor is associated with increasing values of y. Other predictors may have the opposite relationship. Depending on the complexity of f, the relationship between the response and the given predictor, this is extremely important. The relationship between one response and one predictor, one predictor, for example, I don't know, xm, just one predictor, may also depend on the values of other predictors. This is called interaction, where the predictors are interacting with each other. You can't look at each predictor sort of separately from the rest. Can the relationship between y and each predictor be adequately summarized using a linear equation, which is what you would want, ideally, or is the relationship more complicated? Historically, most methods for estimating f have taken a linear form. In some situations, such an assumption is reasonable or even desirable, but very often the true relationship is more complicated, in which case a linear model may not provide an accurate representation of the relationship between the input and output variables. In this book, we will see a number of examples that fall into the prediction setting, the inference setting, or, and this is kind of how I've been treating them this whole time, a combination of the two. For instance, consider a company that is interested in conducting a direct marketing campaign. The goal is to identify individuals who respond positively to a mailing based on observations of demographic variables. So think of age, race, location, socio-economic variables, religion, marital status. The list is never ending. This is if you were to create a census, right? We're looking at demography over here. In this case, the variables serve as predictors, and the response to the marketing campaign, and it's a binary one, it's categorical, yes, no, or positive, negative. serves as the outcome. The company is not interested in obtaining a deep understanding of the relationships between each individual predictor and the response. Instead, the company simply wants an accurate model to predict the response using the predictors. So as long as the model seems to be getting it right, and we'll have to see what we mean by seems to be getting the predictions right. This is one of those exercises where we're not going to go into the why, but why is it that a specific subpopulation of the country is responding in a specific way. All we care about is how are certain people responding, and can we predict that response in the future? Now, in contrast, consider the advertising data illustrated in figure 2.1. One may be interested in answering questions such as which media contribute to sales, which media generate the biggest boost in sales, or how much increase in sales is associated with a given increase in TV advertising. This situation falls into the inference paradigm. Another example involves modeling the brand of a product. Anyway, I think we get the idea. For example, linear models allow for relatively simple and interpretable inference, but as expected, may not yield as accurate predictions. Okay, now how do we estimate F? Throughout this book, we explore many linear and nonlinear approaches for estimating F. However, these methods generally share certain characteristics. We provide an overview of these shared characteristics in this section. We will always assume that we have observed a set of n different data points. So earlier we had n equals 30 data points. It was the employees, right? The workers. These observations are called the training data because we will use these observations to train or teach our method how to estimate F. Now, some mathematical notation. So it's a double subscript. We very rarely have double subscripts at A level, but think of a matrix. Doesn't a matrix have a row and a column? Well, I is your row, and I think I is going to be the observation, and J is going to be a specific characteristic of that observation. So let's have a look. Let Xij represent the value of the jth predictor or input for observation I, where I runs from 1 to n. Those are our observations. And J is the number of characteristics that the model is trying to capture. Correspondingly, now notice why it's a single variable, because it's the output for observation I, represent the response variable for the ith observation. Then our training data consists of x1, y1, x2, y2, but x1 is a vector. X1 is a vector until our very last observation, xn, yn. And we're being told over here, every x over here is a vector. What does that t mean? That t means that, strictly speaking, it's a column vector. So xi1 until xi p. But it's easier to write it as a single, on a single line. It's not a, what's saying us is this is not a point. It's not, don't think of it as a point. It's a vector, but we're writing it on a single line. So you have T for transpose. Our goal is to apply a statistical learning method to the training data in order to estimate the unknown function f. In other words, we want to find the function f hat such that y is roughly f hat of x for any observation x, y. Notice the difference between uppercase and lowercase. Lowercase is raw data. Lowercase is a specific observation. Uppercase is the variable. So y would be, for example, wage, whereas yn is the wage of this nth observation. Broadly speaking, most statistical learning methods for this task may be characterized as either parametric or non-parametric. Let's start with parametric. Parametric methods involve a two-step model-based approach. First, we make an assumption about the functional form or shape of f. So the very first thing, the very first step is a relationship. I think this is our very first formula, right? You would have your model, you know the raw data. So red is what we know. Red is what we know for each observation. We need to determine these coefficients. And if you will always know the red, or well, actually, no, right? I mean, data, there are always limitations. Like if I want to know, like an insurance company, there might be misrepresentation. I might tell an insurance company, I am not a smoker. But anyway, assuming you know the red data and you have the blue coefficients, that's it. That's your formula. That's your formula for any observation, for any data subject. This is a linear model, which will be discussed extensively in chapter 3. Once we have assumed that f is linear, the problem of estimating f is greatly simplified. Instead of having to estimate an entirely arbitrary p-dimensional function, f of x, one only needs to estimate the coefficients from 0 to p, b naught until beta naught until beta subscript p. After a model has been selected, we need a procedure that uses the historical data to fit the model. In the case of the linear model, we need to estimate the parameters b naught until beta p. That is, we want to find values of the parameters such that they do a good job predicting the actual output, the actual variable that we're trying to predict. The most common approach to fitting the model, 2.4, is referred to as least squares. And I'm going to mention Hooke's law again from secondary school. Hooke's law, I think Hooke's law assumes that the relationship passes through 0. Well, yeah, obviously, right? But this would be your would it be one-dimensional? Yes, right? You have y against x1. The model, this would be like what we saw earlier. You pass a plane through the points, right? So for example, at A level, these would be your z, x, and y. but you know, it's very naturally, although you can't really visualize it, it's very naturally extended to higher dimensions. Usually the biggest step, even in one's mathematical development, is learning how to extend a one-dimensional question to a two-dimensional question. Once you've made that step, honestly, I don't know how you feel about it, but including further dimensions shouldn't be that challenging conceptually, just to kind of follow the logic. However, least squares is only one of many possible ways to fit the linear model. And this is your linear model. This is the plane that I discussed just now. Notice it's probably never going to do as good as a job as something like this. It's the same data, but we're fitting two different models. This is non-linear, and this is linear. The model-based approach just described is referred to as parametric. It reduces the problem of estimating f down to estimating a set of parameters. And those parameters are your betas. Assuming a parametric form for f simplifies the problem of estimating f because it is generally much easier to estimate a set of parameters in the linear model than it is to fit an entirely arbitrary function f. The potential disadvantage is that the model we choose will usually not match the true unknown form of f, which is why we had f hat. And I'll just discuss this as a final thing. So for the example that we've just been discussing, where you're trying to model income as a function of years of education and seniority, notice we don't have the error term, but for the simple reason this is just, it's just an approximation. This would really be the expectation, the mean. Maybe I shouldn't use the word average, but I'll say the average. On average, you would expect, given a certain education and a certain seniority, that your income may be modeled based on these three parameters. Since we have assumed a linear relationship between the response and the two predictors, the entire fitting problem reduces to estimating these three parameters, and we may use least squares linear regression. Comparing figure 2.3, which is what I did earlier, right? The two surfaces. The true f, and remember, the authors, they're sort of playing God. They did it backwards. They generated the data points using a predetermined f. So this is the true f. This is the true f. But again, in real life, you will never, I don't think you'll ever know the true f. This is the true f. We're approximating the true f using this model. It's a linear model. You will have decided at the outset, I am going to model linearly. Since we have assumed a linear relationship, the true f has some curvature that is not captured in the linear fit. However, the linear fit still appears to do a reasonable job. Statistics, big part of it is measuring how reasonable is the job that it's done of capturing the positive relationship between positive relationship simply means as the number of years increase and as the seniority increases, then the income increases. Now this is another type of model. It's no longer linear. We're allowing for curvature. And where do we refer to it? A non-parametric approach is shown in figure 2.5. And this is probably a great place to start tomorrow.